Good afternoon, everyone. Thank you for giving me the opportunity to present our research here. The topic I'm going to present today is insecurity of detector-device-independent quantum key distribution. I'm Anqi Huang from University of Waterloo. I'm also thank you for all the collaborators. So let's start from what is detector-device-independent QKD. Before that, we already know what is measurement device-independent QKD. That is, Alice and Bob gonna prepare two quantum states independently and then send to a third-party Charlie to do a bare state measurement. In this protocol, we assume the third-party Charlie can be totally untrusted, so that in this protocol, it can remove all the detector side channels. But there are two drawbacks of this protocol. The first one is the technical complexity, because we require two single photons from different sources and then get an interference. It's still a little bit hard right now. And then the second one is we require the large data block size for post-processing. So we are thinking, could we replace two photon bare state measurement with one photon but 2 bits bare state measurement? The answer is yes. That's why several groups propose a protocol named DDI QKD, Detector-Device-independent QKD. In this protocol, Alice firstly prepares quantum state and send to Bob. Bob gonna encode his information into the same photon, but a different degree of freedom, and then do the bare state measurement. This protocol only requires standard technology, but we can get higher key rates by using normal block size for post-processing. Here is an example of the possible realization. In this scheme, Alice firstly prepare one of 4 BBIT4 polarization states and then send to Bob. Bob gonna encode his information in the spatial degree of freedom and then do the bare state measurement. In this bare state measurement, every single click gonna project to a bare state. That means every detector in this scheme corresponds to a bare state. Over this whole scheme, we assume the gray area in Bob and Alice are fully characterized and trusted. But we assume the 4 detectors, D1 to D4, are not characterized but trusted. Unfortunately, so far, there is no security proof is available. From our research, we found the security of DDI QKD cannot based on post-selected entanglement. Why? The reason is the following. As we already know, MDI QKD is based on post-selected entanglement, so that when we verify the security of the MDI QKD, we only need to measure one bare state. Similarly, if DDI QKD is also based on post-selected entanglement, we can also just measure one bare state over the whole protocol. Okay, if we can do that, then we only need to keep one detector, D1, in our scheme and remove all of the rest of 3 detectors. However, we find it still can hack it by blinding attack. Firstly, it sends a strong continuous wave laser to Bob to blind the detector, and then it's gonna do intercept and resend attack to resend the coherent pulses with the quantum state here. After that, we analyze how much energy arrived to the detector D1 in different cases, as we already showed in this first table. And what if we could have the detection threshold under blinding attack? You see, the value is smaller than mu, but larger than mu over 2. And then we could see what happened in the second table. Bob will only get a click when he chooses the same face as Eve. That means at the end, Eve and Bob gonna share the same secret key. Okay, so far we already know DDI QKD is insecure against the detector blinding attack. by using one detector. Okay, what if we have a full scheme with 4 detectors? We also analyze that, and we find an interesting result. That if Bob and Eve choose different bases, then we won't get any click. But the interesting thing is, if Bob and Eve choose the same bases, we're gonna always get a double click, as we show in this area. So that's it. That's the end of story. No. We have several strategies to avoid the double clicks. Firstly, we can exploit the fact that the detection threshold actually depends on blinding power. Here is the testing results in a commercial system. In this testing, we have 2 thresholds for detector 1, as shown in green curves, and then another threshold for detector 2 in blue curves. And the first threshold we measure is the threshold if the trigger pulse energy is lower than that, we never get a click, as shown in these 2 solid curves. Another threshold is if we could apply our trigger pulse energy higher than that, we're gonna always get a click. That is threshold shown in these 2 dashed curves. Okay, so we testing the threshold under different blinding power, and we find some interesting mismatch. For example, if we could apply around a 0.2 milliwatt blinding power, and then we choose a trigger pulse energy greater than this green dot, but lower than the blue dot, then we only get detector 1 click, but detector 2 never click. Versus if we apply higher blinding power, and we could get only detector 2 click, but detector 1 never click, so that we can avoid the double click problem. Second strategy is also depends on the fact that the detection threshold also depends on pulse timing. We scan the arriving time of our trigger pulse and then measure the detection efficiency. We find the efficiency mismatch still exists under blinding attack, so that we can firstly apply our trigger pulse at T1 to get only detector 1 click. Worse-wise, we can also apply our trigger pulse at T2 to get only detector 2 click. These 2 strategies explore the imperfection of detectors. So we already show DDI QKD is not detector device independent. It still depends on some imperfection of detectors. But also, we could exploit the imperfection of Bob's linear optical network. We could also, by using 2 different ways to avoid double click. As we show in this figure, the figure A in left hand, you could see this is a perfect case that there's no imperfection. We analyze the energy distribution between different detectors by changing the phase applied by E. We find there are 2 curves always overlap to each other. That's why we will always get a double click. But if the phase modulator is not perfect, we can always have some deviation between the real phase and the ideal phase. So we simulate if the deviation is pi over 36, then it could also shift the fixed state a little bit away of the pi over 2 or 3 pi over 2. Then we could get distinguishable energy levels at these points to avoid double click. Similarly, another imperfection we already know is the splitting ratio of beam splitters. In ideal case, the splitting ratio is perfectly 50-50, but we already see we always have some imperfection. The splitting ratio is not always 50-50. So we also simulate this imperfection case, and then we get also distinguishable energy levels between 2 detectors. By this way, double clicks is also removed. From our research result, we found DDI QKD actually is insecure against the detector side channel attacks, as well as against other side channels attacks that exploit imperfections of Bob receivers. But why MDI QKD is secure, but DDI QKD is not? Because it has access to state preparation, so that the assumption about a single photon cannot be guaranteed. Okay, that's the end of the story. Thank you for your attention. Next, my colleague Huang gonna present another interesting topic about laser damage. But before we move on, any questions so far about DDI QKD?
All right, if not, let's thank our speaker again.
Thank you.